we seeing that?
Mm-hmm.
I don't know what happens when I go into full screen. Let's hope it works.
Brilliant, I can see it.
Right, as long as you can see it, Peter, then I'll just start talking and
I see it, that's all that counts.
it's fine. Okay, well, thank you for the invite to talk. So I'm really a spokesman for a large group of volunteers from many different universities, most of whom are statisticians. We have a rogue epidemiological modeler, Leon Danon, in there, who is kind of the focus of what we're trying to do. Also, TJ sort of sits across boundaries, and we have RSEs and other things as well. But mostly, it's statisticians. And oh, why can't I skip slides? That's annoying. Okay, how am I going to skip back? I'll work it out. To the point of what we're doing is not epidemiological modeling, because we can't do that, or I can't. But it's rather taking one of the models and helping to do UQ for it. So it's really helping out, trying to help out a particular modeler. We also would like to be useful for the community that are modeling COVID-19. So everything we're trying to do are to put methods into code that ultimately do the job for the model that we care about right now, but we'll just port over. And then finally, to share all of the simulations and the code with international UQ groups. We've got some really good UQ groups here in the UK, but also in the States and elsewhere. So everything we're doing is on this website. I may flick over to it later. You can get involved and you can go take all of our data and go off and do your own thing. That's really the point of this. Okay, so MetaWards is one of the SPI-M models, as far as I know. I'm not on SPI-M, so I will say things that may be wrong, and it doesn't matter because I'm not there, so you don't have to worry about the impact of me being wrong. MetaWards it's a model, sure. It's SEIR operating in each electoral ward of the country. So I'll just show what they look like here. So I've not plotted Scotland because we don't have a lookup table for Scotland yet. The ONS are coming back to us, we hope. So this is just England and Wales, and if I have time at the end, I'll show you a nice Google map version on this where it's all clickable and you can zoom in. But you can sort of see like that there are about 8,500 or so of these wards. There's the epidemic is going along in them all the time. And then people live in certain wards and they travel between them for work or recreation, and the matrices that drive that, I think, come from the census and so forth. So you can run this model, you can download it, and you can get it from here. We've also got links on our website, and you can run it on your laptop. Although you can't run lots of it on your laptop, let's say. Now, MetaWards is a framework. So really the underlying model that you'll get from the website is this general population SEIR. And TJ especially, and a group of us have worked quite hard to make it the kind of model where we can do UQ, the UQ that we would recognize here on it. And to do that kind of UQ, you really need data coming out of the model that you can compare to the real world. And if there is real data on the number of infected, I don't know how to get it, and it wouldn't be the right kind of thing. So we added to the model, and we put different classes in. So there's a class of asymptomatics, there's a class of hospital patients, and you can get there by you become infected and symptomatic, and then there's a probability you move over to the hospital class. We added a death stage, and we also added critical care. And the reason for doing that is we got the data for hospital admissions, critical care beds, and deaths in hospital. So the idea is you have a model, a big framework, and we do have data we can calibrate it to. Calibrate in the UQ sense. It's quite an overused word. And on our website, you can read about the setup, and you can all of the files for running this version of the model are there. So to talk about the parameters, skipped ahead, there are 6 probabilities for transitioning into different classes. So going back, there's a probability that you move from the E class to the A class, so the probability of being asymptomatic. If you're infected and symptomatic, there's a probability that you recover or you go to hospital. And of course, that one's on the simplex, so we don't need a parameter, and so on. There are COVID-19 parameters. These are sort of, they've kind of been calibrated before, but we're varying them across quite a generous range, things like R0, incubation period, and so forth. There are transmission rates between classes. So how do the people who are asymptomatic infect the general population? What's the rate of transmission there? That's a parameter. And similarly for the other classes. And then we composed a couple of parameters for lockdown. And we've detailed on our website that you can do more and showed how to do it. Our parameters are the lockdown happens when we actually had the official lockdown, and there's a scaling on the force of infection. And then when children went back to school, there's an undoing of the scaling. So these are parameters that we've put on 0, 1. And now you would like to infer these 16 parameters from the model. And how do you do that? And well, I'll show the website at the end, I think. We've had lots of attempts with small ensembles of the model to show standard UQ methods, though it's quite challenging. For the full model, the one I've just described, 16 parameters, we thought, well, let's change, find 200 parameter choices. Because it's a stochastic model, we need repeats. So we'll do 20 of each parameter choice. Why not? So that was 4,000 runs. We'll run from January the 1st, when we seed it in the UK for 6 months. Perhaps more on that later if there are questions. And to run that set of simulations takes 8 hours on 512 cores on a high performance computer. And weeks of work before doing that on an efficient storage method got the file down to 89 gig compressed. We can't uncompress it. It's too big. So having spent 8 hours running the model on a supercomputer, it took me, and mainly TJ, I have to say, about 10 days to get stuff out of it that we could start to do UQ on. So in one of these meetings, I think Professor Ferguson said, these types of models are not like climate models. This looks a lot like the problems I see in climate models all the time. They're big, they're nasty, they take forever to run on HPC. If you really want to do the UQ, there are other ways to run these models, of course. So once we had that, we can start looking at this kind of data. So this model is a serious model. It's never been pushed in this way before. So what does it do when you push it? The sensitivity analysis here is from Jeremy Oakley's vignettes on our webpage, and I've just applied the same tech to this ensemble. Week 12, which is the week of lockdown, and in the Hospital Trust for Cambridge, we see that the most important parameters, I was expecting it to be R0, I have to say. The most important are the probability of being asymptomatic once you're exposed, and the probability of being hospitalized if you're infected. Next, we have the rate that asymptomatics infect the general population, and then R0. And the others kind of do a bit, but not very much. We're going to see what this is all about in a couple of slides. As we move through the pandemic a bit, this is the week that lockdown is released, and we can see that the lockdown parameters had a big effect. These guys are still there, but there's sort of a notion that people might be spending a long time in hospital. Again, this is pure parameters, no data. So this is just the model running with all our daft choices of parameters. And the people in hospital infecting the general population is having an effect too. And then taking it to the end of our simulations, a couple of other parameters have sort of lit up, but it's not vastly different from before. So on our webpage, and in the country indeed, there are lots of ways to try to tackle emulating stochastic models, and we've tried to have a go at various of them. What I've noticed in the ensemble is that for a lot of parameter choices, but by no means all, we have bimodal epidemics, which is to say you have 20 repeats per parameter choice. For some of them, not a lot happens, for some of the repeats that is, and for some of the repeats, things kick off. So in a sense, methods based on means and variances don't make sense, but then there are many wards where things that might make sense. We're looking at quantile emulation, which Evan talked about back in the first of these 3 sessions. So I'll briefly talk about it, but not much. The idea is we'll let M is meta wards, X is the 16 parameter vector that we're changing, and Q is some quantile over the repeats. Now we'd like to model that as a Gaussian process, but meta wards, at least for things I'm looking at right now, hospital prevalence and so forth, that's got to be positive. So a GP is not ideal because it can be negative. And also the probability that a particular ward is 0 is not 0. So that wouldn't go with this either. So instead, I've used a monotonic square root transformation, which doesn't get over all of the problems because so modeling that monotonic root as a GP, it works nicely, but there are still a few too many hard zeros for that to be a realistic model. But the nice thing about this is if you use this inverse, then when you have negative predictions from your GP, like maybe in the 90th percentile or whatever, they're all mapped to 0. So in your predictions, you actually do get zeros, and that's quite useful. And it's quite similar to something that Elaine Spiller and Bruce Pittman have been doing on truncated GPs, but more of that another time. Now, when you try to validate the emulators, things look weird, and I'm going to try and explain what's going on. So here we have hospital prevalences. Again, this is purely over the ensemble. There's no real data here. And we have the parameter, the probability that you're asymptomatic once you're exposed. The black lines here are my quantile emulator. So I'm giving a 95% band with my quantile emulator. And the dots are a left out set of meta-wards runs, colored by whether they land in the band. So the blue ones land in the, I'm predicting well, and the red dots are outside of my prediction. Those of you au fait with UQ would know that I would expect about 5% red dots, or at least that's what I thought. But when I think about it harder, I'm not so sure what it means to predict the 95% quantile, and then to think, should there be 5% outside of those when I'm looking at different quantiles? I don't have the answer. I've been burning too many nights oil to do all of this, and I need some time away to really think what this should look like. But essentially, I'm not happy with it. And Evan Baker and I have probably tried 2 weeks worth of work in the last week, everything we could think of. And this is always what you get. And theoretically, I believe this is going on. Most models I've ever dealt with, mostly climate, yes, there are lots of parameters, but really there's a low dimensional surface in those parameters, and these methods work really well. For this model, because we have lots of probabilities and because there's a sort of exponential thing going on in the underlying epidemiology, there are corners that may be 8 to 10 dimensions in this space, in this parameter space. So when you have, in this case, low probability of asymptomatics, in this case, high probability of going to hospital, high are naught, high rates of infections from the asymptomatics to the others, and so forth. You can see how you can get towards a 10D corner and get a really big epidemic. And if you have an infinite dimensional GP, what they are, if you want to try to constrain 10th or 11th order interactions with 200 data points, you probably won't. So I think that's what's going on. I think that the surface is quite complicated. So the question is, can we use it? And if you look at the scale, the answer is there is no way that hospitalizations in week 12 were this high anywhere. And checking this with Leon and our data, that's fine. So what seems to be happening is our emulator says it's really high, and it is usually higher than our emulator. So we should be able to use that in a history matching sense to cut that part of the space out. And if we can cut the space where there are really vigorous epidemics that don't make any sense with the data, then we should be able to run more models where it makes sense. And speaking to Leon, that should be around here. And get a much better validating emulator when we're able to pick out more of these interactions because we have a higher density of runs. So having done lots of offline sanity checks, we're not ruling out things in a bad way with this, but it is interesting to note why it fails. There's a UQ challenge here that I don't believe is solved. Okay, so we have this for GPA and for R0, and the slides will be available. Now, so I want to constrain the model to data, and I've got a quantile emulator, and there is no such thing as history matching with quantile emulation yet. So the idea is to say that the data that you see is the model at some best parameters, that's the normal bit, and at some quantile plus discrepancy and error. So you hide the quantile just in the model, and you don't presume that the real world is random, which is an interesting approach. The bonus of that is you can calculate the implausibility. Remember, large implausibility means you rule out. Low means it's not ruled out yet. However, you don't really have this expectation variance from the GP as normal. So you have to do some integration because you've got that nonlinear transformation. Fortunately, because this distribution is Gaussian and you know the mean and variance, this is from the GP. That is a lightning fast integral even by Monte Carlo, but you could do something better. It's also 1D and similar for the variance. So actually we can get very fast prediction and fast implausibility, which means we can map the space. So before I map the space, I have to tell you how I'm going to calibrate. I'm just looking at hospital prevalences now. This will come a little bit later. Just weekly prevalences at trust level, not ward level. I'm going to set the observation error. So I have the daily observations from SPI-M. I'm not going to show the data, so that's why I don't mind recording. But I am going to assume that they're corrected reports. So I believe that the standard deviation should be about 1 on any given day for a hospital, which means it could be like plus or minus 3. I don't know if that's a real thing, but it's my judgment, and it's fine for now for cutting out the big epidemics. And then when it comes to discrepancy, and I've done this for climate models for a long time, I don't necessarily agree that you always have to spend months and months embedded with the modeler to find the actual discrepancy to be useful. And I don't think the alternative to that is just, oh, plus or minus 10% either. We always try to say, I want the discrepancy such that the model kind of looks right, or it looks like it's doing the right things, and I won't worry too much about the numbers. My way of getting to that here is to say, okay, well, let's look at the order of the data and say, I want to have across the UK the right shape of epidemic. So when the data is small, I want my model to be small. When the data says we've got a large epidemic, I want the model to be large or of the same order of magnitude, but I don't care so much about the number. I just want the shape to be right. And of course, having this kind of tolerance to error approach means you keep models that are consistent with this. And if you want to revisit it later, you can just rule out further models as long as you're constraining it. So one key to this idea is to try to be conservative. So just a quick look at some of the results just for week 12. So our 200 runs with 20 repeats buys us about 30% of a reduction in space on 1 week's data. And to look at these plots, if you haven't seen them or been at the other sessions, the idea is if you pick a pixel, I'm hovering over this near white part in the corner, that is showing you, the color is showing you the proportion of points behind that pixel in the other, I think it's 13 dimensions or maybe 14 dimensions. The proportion of those points that are still in. So basically it's saying when it's white over here, we've cut out most of this corner of the space. So epidemiologically what's going on, it's saying, well, when the probability that exposed become asymptomatic is low, and the probability that the infected symptomatics go to hospital is high, we're ruling out most of that space. And if you recall, that was where we had the really big epidemics. So things kind of make sense. You can layer this up. So doing so for, I'm sharing my screen. I hope you don't see the Zoom things in the way of the title. I don't really know how to remove it either. So if you are, I'm sorry, but I think it says 55% of space removed. You see the same sorts of things. There's a little bit of interesting structure with lockdown. And to be honest, we need to sit down with Leon, and we'll probably spend a long time just talking about the structures here to sanity check them, but they mainly make sense. So high R0 is not really possible if we have this low rate of asymptomatics, and you would get big infections, but it is possible if you had high rates. And that doesn't mean it's real, it just means that that's what we've been able to cut out of the model just with the hospital prevalences. Okay, so moving on. Oop, skip too much. So I picked a model that's in our NROI space that meets our targets, and I'm running a movie of the simulation. So now this is meta wards with a consistent epidemic. We seeded it just in London, so it starts there. You see it dies back after lockdown. And then when our lockdown release thing happens, it comes back a little bit, and it comes back in a more sort of spatially aggregated way. It's not so much localized to London. And I'll be putting these movies on the website soon. I have one for asymptomatics at the end. This one's nice. This sort of shows the hospitalizations where you bend the area of the hospital trust by the number in there. This is quite a nice little video, and you see how it starts off really bad just in the southeast, and then things sort of spread across the country, and things even out a little bit more. I do have a movie somewhere of the asymptomatics, and I show it at the end if people are interested. And I just want to quickly say something. So Ben Youngman has done a quick analysis looking at deaths. So this is a binomial type calibration where you say the deaths at a particular trust and a particular time are binomial, with the number of people, the population being those that were in hospital at that time, which is kind of uncertain, and some probability. And then you have the same in the model, and you try to get the X to match that probability probabilistically. And he did that this morning, I mean, literally this morning, without any constraint on the hospitalizations, so you should ignore this part. But it kind of shows that to be consistent, this probability of recovery if you're in hospital needs to be high, and the probability of recovery from ICU needs to be high. But I guess a little bit of a grain of salt is needed, because I think you need to calibrate the number of people in hospital for that to be good, or at least do the two in tandem. So I'm sorry, this has been a tour de force, but time is short. Some conclusions. A spatial COVID-19 model is actually a lot like a climate model. They're expensive to run. There's a lot of parameters. The response is nonlinear. You need some HPC. You need some clever data storage. I don't have any of the latter yet, but we're working on it. And it takes a while to change your model to running in UQ mode. So readying any model for real UQ like this is a big job. You really need to start before an epidemic. I think we've been doing this for over 3 months, and I must have spent the last week doing all of this analysis, because everything else has been problems with setup. It's a hard thing to do, but it is worth it. It's just not something you can do on the fly. In terms of this analysis, there are lots of things to do next. We never just run one wave of a model. And as I've said, we've cut out a lot of the big epidemics. The next step is to run where the smaller ones are, and we do it again and again until we start to get good calibration. And that will help when you have something that's nicely calibrated in that way, and it's calibrated spatially, then we'll be able, if there are local outbreaks, to use some data assimilation, which is planned, to look at the effectiveness of local interventions. So that's how we will endeavor to be helping Leon going forward. But obviously there's a lot of work to do to get this sort of tech working in real time. And whilst it's lovely to have UQ sessions, and I've talked in many of them and said, oh, we can do this, we can do that for models. In this space, I just don't think the off-the-shelf methods are there. And I think we've tried them all. And I've also tried 10 things that I know and have planned, and they don't work yet either. In a way, that's nice. There's research to do. There are UQ challenges here. So if you are interested and you do UQ, the data and code is here. To get started, to get the data matched up to trusts. And we'd be delighted to accept vignettes on our website, fold you into the project. There is no money, there's just some interesting problems and lots of data. So, oh, and if you don't like our version of MetaWads, we've given you a roadmap to writing your own and running that too. And a few references to close.
Thank you, Danny. I can find a little button I could clap, but I can't. Okay. Are there any questions for Danny? There will be a chance to discuss things at the end. So.
Oh, Michael's forehead has appeared.
Hi.
Is that a question, Michael?
Yeah, I could ask. I mean, I'm always interested in the difference between the model and the world, the model discrepancy. So you don't want to spend 3 years, down the pub with the modelers, they're sort of doing this. Yeah. Okay. So obviously you did a thing, and is it based on your gut feeling that the model is kind of good? Because it can do kind of things. Because I mean, there are ways of exploring that. I mean, particularly questions like, if it gets this thing wrong, how likely is it to get that thing wrong? Which things we know are missing, and we know, and they are bound to be important. Which things you could do. I mean, I always find that doing the internal discrepancy things shows me stuff that of an order of magnitude different to what I thought. And in particular, questions about beliefs about, errors in the past and how they relate to sort of forecast errors in the future. So is it you just didn't do all that because time was short, or because you thought, well, never mind that, life goes on?
I think that stuff becomes important at some stage when you go out of the phase of this tolerance to error phase. But I really don't think you can do nothing until you've done all of that, if that makes sense. So cutting out the really bad stuff with the argument that if the model were to predict things that were just that far out of whack, then you wouldn't have gotten to SPI-M in the first place, and nobody should listen to you. You would like to find out. Most modelers I've worked with would like to know if their model can reproduce roughly the right thing. And roughly the right thing is a subjective thing. I understand that. It's not clear what you should do. But I think there's a very strong argument to say, if you're tentative at first and you try to make sure there's discrepancy there that keeps the right sort of thing and doesn't overcut, but doesn't have to go into too much detail, then what you get after a few waves of that is a modeler that's much more engaged and much more understanding of why these few features that the model isn't getting right are there. And so you actually have a more productive discrepancy conversation, and you can start to do those experiments when little tiny tweaks don't lead to epidemics that just don't make any sense and burn through your HPC time. So I think there's a place for that preliminary set of things to do before you then go in and say, okay, we're going to do this calibrated prediction now.
Yeah.
Now it's for serious.
Of course, it does rely on the first few ways actually cutting space out without relying on the correlation between the errors in different outputs. Or are you saying that you put shape in as a kind of a heuristic tolerance to error thing?
It's that heuristic thing, right? So the shape is sort of coming from the data, and the models that don't have the right shape, the right-ish shape, and I've made sure ish is very much in there, don't go through.
Yeah.
But yeah, it's a complicated question. I guess my take is that you can address it in stages rather than having to do everything before you do anything.
Fine.
Any more? Okay, thanks, Danny. Next up is TJ.
Hi, Peter. Thanks. Right, I'll just try and share my screen. Hang on. Excellent. And okay, cool. Can everybody see? Can everybody see my mouse moving around?
Yeah, that's fine. I can see your mouse and your screen.
Perfect. Okay, cool. Thank you very much. Yeah, thanks for the invite. I just wanted to talk really a bit more sort of, I guess, a practical talk, just talking about some of the, well, a comparison really of approximate Bayesian computation versus history matching for trying to fit these sort of very complex sort of agent-based simulation models. So, I mean, within the kind of statistical inference field of epidemiology, there are some really, really nice likelihood-based, particularly Bayesian inference approaches for fitting these kind of complex systems. But because we have various issues like the fact that we never observe the right type of data, that we have to have a lot of latent variables and other things kicking around. And this makes it very, very challenging to try and scale these inference techniques up to more complex models, and it requires quite a high entry level of knowledge before you can start getting into those sorts of things. So over the sort of last maybe 20 years or so, there's been a kind of explosion in kind of alternative approaches, particularly ones that rely on simulation. And there are lots of different versions of this, and ABC is a kind of is a sort of colloquial term for a whole range of different techniques. But in a sense, what they do is they approximate likelihood functions using simulation. And this is very attractive within epidemiology, because nearly all of the models, particularly the complex models that people are generating, are simulation models. And so in some sense, you can use the simulation model directly in your inference routine, and that is very helpful. The problem is that even in kind of small scale systems, ABC is not very efficient, so it can often require hundreds of thousands or even millions of model runs. And this is fine if your simulator is very fast, but it can be problematic if your simulator is slow. So there are lots of different ABC approaches. I'm just going to talk about one which is fairly common and is reasonably efficient in the general scheme of things, and that's the ABC sequential Monte Carlo type approach. So the idea here is that, so if we look on the left-hand side here, what we're going to do is we're going to take some parameters, and then we're going to simulate from our model. And we're going to put some distance measure around the simulation and the data. So in this plot on the left-hand side here, I'm going to imagine that I've got a time series of counts. So each dot here is a data point. And what I've just done here is I've just put a region around the data. And so basically when I do a simulation, if my simulation lies within this region, then I would say that that's a match. If not, it's a mismatch. So in this case, we approximate the likelihood by giving it a value of 1 if you match, or 0 if you don't match. And essentially the size of the region around the data, or around some summary statistics of the data, is defined by what we call the tolerance. And if we have a larger tolerance, then we match more loosely. If we have a lower tolerance, we require that the simulations are closer to the data. And so the inference problem comes in the sense that, so if we look on the right-hand side here, what we're trying to approximate is this kind of, is our target distribution. So it could be an approximate posterior distribution of some description, which is given by this dotted red line. And the way that we're going to do that is to generate a whole bunch of particles. So each particle is a parameter set. And effectively, we simulate from, we sample lots of times from the prior. For each parameter set, we simulate. If we get a match, we accept it. If not, we reject it. And we carry on doing this for a fixed amount of, until we have a fixed amount of matches. And so what happens is that if you notice, so this is in the top here is the prior, and after I've gone through this stage of matching, what I get left with are a bunch of accepted particles on the bottom here, and these are an approximation to the distribution that we're targeting. Of course, it's not a very good approximation here, right? So this black line is the sort of approximate distribution, and it's not very good because we're matching very, very loosely to our data. So the way that ABC works is you tend to then run this through a series of stages where at each stage we reduce the tolerance. So for example, this is second generation, we make the tolerance slightly smaller. And then what we do is we resample these particles at random, we add some noise to it, and then we simulate. So at the next generation, you should be getting particles that are spread around the space according to the previous distribution. Okay, and we continue this process here, and so now you can see that we're getting particles that are looking a bit more like the red line, and we continue this through a series of stages, and then what we should end up with at the end is effectively a set of particles in the right region of space, which we can use to approximate this target distribution. And the efficiency of this algorithm is a trade-off between the number of particles that you have and how much noise you add and how you make these transitions. So just to show how this works, so this was a big HIV model. I'm not going to delve into the details of the model because it's not really important, but it's an individual-based stochastic microsimulation model. This particular version has 22 parameters and it has 18 summary measures that we were trying to calibrate to. And the problem here is that this model takes anywhere between sort of 5 and 10 minutes to run a simulation up to upwards of 3 hours in some parts of the space. So the cost of doing the simulations is very high here. So this is what I'm showing you here. So these are the 18 data points that we're trying to calibrate to. Don't worry too much about what they are, but the dashed black line here is the actual observed data point. And the gray region just corresponds to some measure of observation error. So we're happy if we get simulations close to this gray region, in essence. And the densities here correspond to the simulated outputs for each of our accepted particles at each generation. Okay, so you can see that the earlier generations of the lighter colors, and that's when we had a larger tolerance around this, so we accepted across a wider range of outputs. And what happens is that for most of these outputs, as we go through the ABC, the different generations, you can see that it seems like it's converging quite nicely towards the data point. However, we do get some odd ones. And so particularly this one is problematic because at this point, it's very clear that the simulations don't look anything like this data point. And this is a problem, right? Because if we want to use this model for inference or for forecasting or whatever it is, and it doesn't fit the data, then that's problematic. Now, the issue here is that there could be multiple reasons why this doesn't fit the data. So one reason could be that the model itself is just simply not capable of fitting the data, which is then a problem because then the model is not very good and we should discard it. Alternatively, it could be that we just haven't found the right region of parameter space yet. And that becomes a more difficult problem because, of course, we have to then decide, well, do we keep running the model or not? And one way that we can sort of explore that a little bit is to look at some plots of the acceptance rate and the tolerances. So what this left-hand side plot is that you've got each of the generations of ABC along the x-axis, and the y-axis is a scaled tolerance. So 1 here corresponds to the tolerance at the beginning in the first generation, and 0 is where we want it to be. Okay, and you can see that most of these outputs we're getting relatively close matches. But this problematic one, which is this dashed blue line here, it looks like, you know, if we were to extrapolate this forward at this rate of convergence, it would take many, many, many more generations to hit, to get anywhere near to the data. And if you look on the table on the right-hand side here, this is the acceptance rate. So here, what we're trying to get is 22,000 matches. And you can see that as we go through the generations, our acceptance rate is only about 15% in the last generation, which meant that we had to run the model about 143,000 times in order to get 22,000 matches. So you can see that the combination of these two things means that this could be a lost cause in terms of us continuing this, because at this point it had taken several weeks on a HPC. And so this is a quandary, and it's difficult to get out of this with ABC. So want to then just compare this to using history matching. So we've seen a lot of this, so I don't have to spend a huge amount of time explaining this, but essentially what we're going to do is the same sort of thing that Danny was talking about earlier. We're going to use an emulator, and history matching aims to try and use the emulator to explore the space and then to rule out space using the implausibility. And the implausibility measure, so e to the theta here is our prediction from our emulator. So the numerator here is some kind of measure of distance between our data and our prediction. And then we divide through by all the different sources of uncertainty. And we retain bits of the space where the implausibility is low. And the implausibility can be low either because the emulator predicts a good fit or because there's a lot of uncertainty. So we're not sure what's happening. And again, history matching proceeds through a series of waves. So this is just a one-dimensional schematic. So this time the x-axis here is the parameter space. The horizontal solid line is the data point, and the rectangle corresponds to the observation error. So in this example, we've run the complex model at, say, 6 points in the space. We've trained an emulator, and then we run the emulator. So the blue line here is the emulator prediction, and the red bars are the uncertainty bands. And so for each of these points that we run the emulator, we can calculate the implausibility. And so even though we have areas where the emulator is uncertain, we can still remove bits of the space. So at the end of this stage, what we have is a green space down here, which basically represents the area that we haven't ruled out yet. And so the reason why we haven't ruled it out is either because there are good fits in that space or because there's more uncertainty. So what we then do is we can target more design points. So for example, I can put a design point in here, and this tightens up the emulator, and then we rule out more space, and we continue this basically until the emulator or the emulator uncertainty is small enough that we don't have to worry about it too much anymore. And then when we finish, what we can then do is run a series of simulation designs within that non-implausible region and compare that to the data. And so that's what we get here. So this is pretty much the same plot as the ABC. Similar sort of idea. As you go through the waves, we get better and better matches. But in this case, if we look at this problematic one, we can see that it was in fact possible to fit this particular data point using the model. The reason why the ABC didn't find it was because we couldn't find the right region of parameter space. And the reason for that is because the region where we get the good fits is a tiny, tiny fraction of the original space, right? Because it's a 22-dimensional space. And the emulator allowed us to find it. And furthermore, at this point, the history matching was using about half the number of simulations. But bear in mind that for the ABC, we would have had to have run it for potentially millions of simulations to find this region. So it potentially is a much more efficient way of looking at these very large scale models. There's lots of reasons why we might want to use this, and it has some nice properties. Just focusing on the two bottom ones. So the one of the challenges, of course, as Danny has looked at earlier, is the fact that ABC is attractive because it sort of works automatically in some sense, right? I mean, I never like that, but the idea is you can plug it in and to your inference routine, and then you get some answers. But history matching relies on you having this good emulator, and that can be very challenging for these sorts of models, but it potentially allows us to solve problems that are difficult to solve using sort of classic ABC. And there's lots of people involved in this work, so thank you very much. Sorry, I think I'm slightly over.
Okay, that's okay. We're all running a little bit late. So any questions for TJ? No blue hands, any real hands? No, can't see any real hands because no one's got their video on. So thank you, TJ. Thanks very much.
Thank you.
And I've worked out how to do that. So who's next? Simon, are you there?
I am, yes.
All right, can you see my screen?
Yes.
Okay, well, thank you for having me. I'm also not going to be talking about COVID today. I'm going to be talking about a project that we've been working on to develop multi-model ensemble modeling techniques using foot and mouth disease as a development case study. So I don't really have to give much introduction to this, as I think many people have already done so very eloquently today. But we know that different models make different, sometimes disparate and inconsistent predictions for a variety of reasons. And this can be particularly difficult when we're thinking about a policy context where decisions are going to be made based on models, and determining how you choose which model you trust most in a given situation can be challenging. So ensemble modeling is a way to combine projections from multiple different models into a single interpretable forecast. And this has been used a lot in different fields, including climate change projections and weather forecasting and hydrology. And in those fields, multi-model ensembles have improved the robustness of forecasts and the accuracy. So we've been developing a ensemble technique for an epidemiological context, and we specifically chose the Bayesian Reliability Average Ensemble Method, or BRIA. And I'm not going to have time today to get into a lot of the technical details of that, but if you are interested in hearing about those, they are detailed in the Lindstrom paper from 2015. So there's a couple of reasons why we picked this particular ensemble method. And the first reason is that it works on relatively small amounts of data, which is ideal for an epidemiological context where we have much less data than you would for such as something like weather forecasting. It also runs on summary statistics. So these are things that include the number of infections or the number of vaccines given out. So the type of information that is often collected in an outbreak situation and is easily output from a number of different types of models. The other nice thing is that it does not require parameter fitting to data. So you can fit parameters to data, but you do not have to, which means that you can look at it in situations where you have no data. So you can compare like an implemented control policy to one that you might want to try an alternative control policy to see how they would compare in the future or looking retrospectively. And it also can speed up the process if you're dealing with very large simulation models with a lot of parameters, where parameter fitting the possible is technically challenging and can be time consuming. So this is a hierarchical Bayesian model, and the model weighting in the ensemble is done by two different criterions. It's done by a bias criterion, which looks at how well each model in the ensemble predicts the observed data, and the convergence criterion, which looks at how well the models match each other. So this would downweight outliers. We can also incorporate expert opinion to give higher weight or lower weight to certain models, but we have not done so in this particular study. So again, I don't have time to go into all the details, but this is just an overview of how this process works. We have some outbreak data, which is shown here in red, and this can be used to estimate parameters, but you don't have to estimate parameters. Models can use their default parameter values as well. Models are simulated independently of each other using their own best practices, and they can initialize those simulations with the outbreak data. From the individual model simulations, which are represented here by the M1 to M3, we pull out outbreak quantities such as the number of infections, or in the case of foot and mouth disease, the number of cold farms. And we can do this at multiple time points. So if we want to look at a past time point and project into the future, or we can look at an implemented control policy and compare that to an alternative control policy. These outbreak quantities then get input into the BRIA ensemble analysis, which weights them based on the bias criterion, so compares to the data from the outbreak, and the convergence criterion, which is how well they agree with each other, and this provides the ensemble projection. And what I'm showing here on the screen is just a univariate example where we have one outbreak quantity, but this method actually does work in a multivariate context. So we have multiple outbreak quantities going into this analysis together. So we use this method and asked using FMD as a case study with limited data early in an outbreak, how well does this multi-model ensemble forecast the future of that outbreak? And this is work that is highly collaborative with a lot of groups from around the world, which this would not have been possible without their input and support. So we're using foot and mouth disease to develop these methods. It's a highly infectious viral disease that affects some important livestock species, including cattle and pigs and sheep. And we're using two sets of outbreak data for this analysis. We have the fairly well-known 2001 UK outbreak, which was a national scale outbreak. And we also have the slightly less well-known 2010 Miyazaki, Japan outbreak. And this one was quite a bit smaller as it was confined to the prefecture of Miyazaki. And as you might imagine, the infrastructure is quite different in these two outbreaks, as is some of the agricultural practices. So they're fairly different outbreaks of the same disease. We are including in this preliminary results that I'm going to be presenting, we're including 4 different established FMD models that have been used in policy around the world for a number of years. They're all stochastic simulations, but they are all independently developed and also make different assumptions about the mechanism of transmission and about control as well. So the models we are including are AdSim, Ospread, DADS, and Warwick. And this is just a preliminary set. We are going to be adding an additional 2 models for these outbreaks. Okay, so the way we set this up was to simulate, in some effect, an outbreak situation. So the models are going to be run with controls that were implemented in the 2 respective outbreaks. And they're initialized with the data 2 weeks, from 2 weeks after the start of the control program. So they're given 2 weeks of data, and the start of the control program for both of these outbreaks falls just after the official first report of the infection. So they are blinded to the rest of the outbreak data. They are not given that data. And then we use a couple of outbreak quantities in the BRIA analysis. For the UK, we are preliminarily using the number of infected premises and the number of cold premises. The same 2 quantities for Miyazaki with the addition of vaccinated premises, as vaccination was part of their control program. Okay, so I'm showing preliminary results from the 2001 UK outbreak, and I'm just going to orient you to these figures because they're going to be the same type of figure for the Miyazaki outbreak as well. The y-axis shows the log 10 of the number of infected premises on the top and cold premises on the bottom. And the x-axis shows the time point in the outbreak. So 4 weeks post-control means 4 weeks after the start of the control program. So as I said, we're giving them 2 weeks after the start of the control program. So the models at this point will have been running blind for 2 weeks. The red lines on the plots are the observed data at that point in time. But again, the models don't see this data, neither does the ensemble. This is just there as a reference point. The individual models, which are in no particular order, so they're not alphabetical or anything, are the gray dots and bars showing the range of their stochastic simulations. And the ensemble posterior predictions are given by the black bars, with the horizontal line being the median posterior, and the thicker part of the vertical bar being the 50th credible interval, and the thinner part of the bar being the 95th credible interval. So what we're seeing is that overall, and maybe more consistently, the ensemble has been able to capture the outbreak data better than any individual model alone for both sets of quantities. So this outbreak is fairly well known, as I said, so we're also interested in looking at an outbreak that is much less studied. And so we looked at Miyazaki, Japan. And again, we have infected premises on the top and cold premises on the bottom. We can see that for this particular outbreak, there's quite a bit of more uncertainty in some of the models themselves. And the ensemble is still more consistent at being able to capture the outbreak data than any of the individual models by themselves. I'll also say that we've found that the models do tend to do better or worse for some outbreaks, and sometimes do better at certain quantities than others, which this ensemble does take into account for. Okay, so I don't have time to go into any additional results, but preliminary conclusions are that this BRIA methodology is a good framework to continue developing as a multi-model ensemble technique in an epidemiological context, and that it does work with different types of models and limited data. It also is able to incorporate different levels of uncertainty in an intelligible way and provide a easy to interpret prediction. And our preliminary results suggest that the multi-model ensembles could be very useful in early outbreak situations. So with that, I would like to thank the many people who are involved in this project, particularly the modeling teams and folks who helped with data acquisition, and our funding agencies. I'd be happy to take questions if there are any.
Thank you very much. Have we got any questions?
Can I ask a question, Peter?
Yeah, of course you can.
So thank you. That's a very nice talk. It's very interesting. I was just interested in the criteria you used to combine these models together. So did you refer to it as the convergence criteria? If I understood what you said correctly, that would downweight models which are kind of outliers and upweight models that are kind of similar to other models. Now I can see your thinking behind that, but I can imagine a class of situations where that is a very good idea. Do you worry about the other class of situations where, for example, say, if you were to use quite a few groups models, you might have, say, 5 groups who have made the same scientific underlying assumption, and maybe it's an incorrect assumption, and they will all cluster together, but they all cluster together for one reason, and that reason is because they're all a bit wrong. Do you worry about that criteria in that situation?
So yes, obviously that would be something we would need to think about. That is somewhat mitigated though, because we're using 2 criterion simultaneously to weight the models. So we're not just looking at the convergence criterion, we're also looking at their agreement with data. So if there's a group of models that is clustering together, but is quite a bit more off, let's say, than a model that is an outlier, but is agreeing with data, the model that's the outlier will get higher weight because it is agreeing with the data. So we do have some, I guess, checks in there as far as that goes.
No, that's very good. That's very good. That's nice. So a group of models that looks okay so far, and but then all makes the same incorrect prediction for the next time step. That would be the problem. But no, I like what you say. You say you have 2 criteria, which at least guards against some of that. That's cool. Thank you.
Yeah, and the ensemble also does learn or gain weight from the other quantities that are included. So if we have IPs and we have culls and you have vaccination, it does take into account how those are not fully independent of each other. And so it's looking at those relationships as well. So it's obviously it's not perfect, but it is a nice, I think, maybe I'm biased, a nice way to at least in a way that doesn't require a lot of parameter fitting and really heavy computation, combine models in a specifically weighted context.
Thank you.
Okay, any more? Can't see little blue hands. Great. Okay, thank you very much, Lindsay. So our next speaker is Mike Tilsley. Mike, are you around?
Yeah, I'm here. In a minute. I seem to be having some slight laptop problems, so I'm trying to share my screen. Just bear with me.
Don't worry, we all have laptop problems at the moment.
It's just decided to misbehave.
They always do.
I don't know whether this is even working. Ooh.
If it helps, Mike, you can always email the slides to me and I'm happy to to just do the screen share bit if you want.
Yeah. It's technology issues always get you. Okay, so so I'm going to talk about some work that we've been doing on real-time decision making. Now, first of all, a big thanks to Lindsay, because Lindsay's done a lot of my work for me by providing some really great background on some of the FMD modeling work. So it saves me quite a lot of time. One of the things we've really been interested in is, over the past few years, is really looking at the utility of models in the early stages of disease outbreaks. This is really based upon the idea that sort of a lot of years ago, really, generally what many people in the epidemiological community, myself included, really did work on retrospective modeling. So typically what we would do is we would look at control policies focusing upon what we could have done to reduce the impact of an outbreak that had already happened. So we might take an epidemic. Now, again, this is the timeline of the foot and mouth disease outbreak in 2001. We would fit our model to the data retrospectively, and then we would then look at a particular control policy. So we'd say, what might have happened had we have vaccinated in 2001 rather than done a severe culling policy that actually happened. Now, of course, in reality, what's really most useful for us really is to try to look at the impact of these models in real time. And it's particularly relevant, of course, with obviously the current pandemic. So this led us to think about looking at using these models in real time, but using the 2001 outbreak of foot and mouth disease as kind of a dummy real-time epidemic. So at some point, of course, during an outbreak, we're going to resolve uncertainty, but we can't afford to wait for that uncertainty to be resolved before we make a decision regarding control. So what we're really asking ourselves is, how can we determine the best control policy to put in place on day one, given that we've got this uncertainty at the start of an outbreak? So we've got sort of a learning phase where we're trying to resolve uncertainty. And then we've got, and I put this in parentheses, an optimal control phase where we've resolved that uncertainty and we, in inverted commas, know what the best thing to do is. So, of course, at the start of an epidemic, we have uncertainty. So we may have a model, but we don't know what the parameters are. So I'm not going to go into detail on the model, but this is the Warwick model that's been used for many years to look at foot and mouth disease. And obviously, there's a bunch of parameters associated with the infected farm. There's a bunch of parameters associated with the susceptible farm. And then we have basically a power law function that determines risk of infection based upon distance between infected and susceptible farms. So this is what we're trying to fit to the data. So basically what we're trying to do is we've got a bunch of data, we've got some control strategies that we want to analyze, we put these into the model, and then we get a prediction of these competing control strategies. And we have a metric that we're trying to optimize. Now here, of course, I'm giving an example of outbreak duration, but it could be number of farms infected, it could be number of animals culled, etc., etc. But if we're using this in real time, of course, we're putting in the data at a specific point in time. We're projecting this forward, and we get a prediction from the model of what these competing control policies do. Of course, after an epidemic, we have the luxury that we can use all the data, and we can go back and we can fit the model, and we can get a perhaps different prediction of what the different control policies would do. And that's what we're really interested in analyzing. So the key question is, at what stage do our model projections and associated control action recommendations become resilient to this accrual of information? So we're going to look at two scenarios here. In the first one, what we're going to do is we're going to sequentially fit the model to the data on weekly intervals. And every week we project this forward and we get predictions of what the model will predict in terms of the competing control policies. So here we can see in weekly intervals a schematic what we might get. And then, of course, we can do this all the way to the end of the epidemic. And as we get more information, of course, we get better understanding of the impact of the different interventions. So these forward simulations here are based upon accrued knowledge. But as a comparison, we can compare this to what we would get if we fitted to the entire epidemic, but projected forward from the state at the particular point in time. So we can say we've retrospectively fitted to the entire epidemic, and then we take our state on, say, the 26th of February and project forward from that point. And we can get a different set of predictions if we were fitting it retrospectively. So we would say these simulations are based upon what we might call perfect knowledge. We've done the epidemic, we know everything, in inverted commas everything, and we have a prediction of what the control policies might do. Okay, so first up, this is just sort of a very example. In the very brief time I've got, this is just to show you the parameter variability if we fit this model sequentially, only using the information up to that point in time. And this is just one example of one particular parameter, which is the exponent on cattle transmissibility. The key thing to take here is that in the very first few weeks of the epidemic, we have quite wild variation in terms of our model predictions, and it takes quite a lot of weeks before this prediction settles down. So that's quite disconcerting. So these model parameters are poorly predicted early on, but what about control? So we're going to look at 6 competing control strategies, and these really represent kind of incremental increases in control that we're putting into the system. So initially, we're going to look at only culling infected farms or culling infected and high-risk farms, which are what we would broadly call risk-based, which on the next slide you'll see coloured in blue. We're going to look at some proximity culling, which on the next slide you're going to see coloured in green. And we're going to look at some vaccination strategies, which on the next slide you'll see coloured in red. And we're going to see what the impact of these different policies might be. Okay, so the first thing we're going to look at is what would a retrospective model advise? So if I fitted to the entire outbreak and then I go back and project forward from individual weeks. So this is my hindsight prediction. And we can see that actually it's really striking. If I have perfect knowledge, then it's really clear on week 1 what the best policies are. It's clearly best to vaccinate. It's clearly worst to only cull infected premises. That's clearly the worst policy if we fit to the entire outbreak. Now some bad news. If I then compare that to my accrued knowledge prediction, unfortunately, we find quite a different state of affairs, that early on, all of the control strategies have a very, very similar impact of the epidemic. And it takes quite a few weeks before that uncertainty is resolved. And if we think about this from a policy perspective, there may be a pressure to choose the least severe strategy, which actually we know is significantly worse than other strategies. So we asked ourselves why this might be. And we went back and we looked at the model predictions of where the epidemic was through time. And if we try to fit this, we find that in week 2, the model predicts that essentially the epidemic is everywhere. So the darker the county here, the more infection there is. But the model predicts in week 2 that the epidemic is everywhere, whereas we can actually see from the complete information on the right that there's several counties, particularly in Scotland, where the epidemic is not spreading. By week 3, the accrued picture is becoming much closer to the complete picture. So it takes that length of time before we get a good spatial prediction of where the epidemic actually is. So this was interesting. So I'm just going to conclude with some slightly better news. If we then rank control policies, now this is, the caveat here is this purely ranking them on the mean epidemic size. If we rank them on a weekly interval as to which is the worst and which is the best, it's actually quite striking that both the accrued and the perfect knowledge model give IP culling only and the risk-based culls always coming out as worst, and these vaccination policies with some slight variability always coming out as best. We do get this slightly weird phenomenon that ring culling, which is the dark green one, actually becomes optimal late in the epidemic, because at that point we're dealing with small isolated clusters that ring culling can eradicate rapidly, where it's not very good early on, which is why we see that coming out. Okay, so I think the key thing to take home here is that these actions, these control actions, if we purely based on the mean, are quite robust, but our magnitude of projections are initially estimated very poorly. And the key take home is that state-specific control is really quite crucial. Just as a caveat, and I'm literally just going to show one final picture of this. We have been looking at similar things for COVID, and this is our schematic of Matt Keeling's model for COVID-19. And I'm going to skate over this because of time, but one of the things we have been looking at is looking at adaptive relaxation of lockdown. And in these slides, we can see we have a situation where we relax lockdown measures, but we reintroduce them basically if intensive care unit occupancy exceeds a certain threshold. So it's sort of in a similar way that we're having bespoke policies that are introduced based upon the state of an epidemic. And this was something we looked at in early May. What we concluded here was that what we did get was a long epidemic tail if we looked at this kind of adaptive relaxation policy, which stretched out well into 2021, but we didn't get a significant peak. So I'm just going to leave that there as just a food for thought. Whole bunch of people to acknowledge that have assisted with the FMD work, and of course there's a vast Warwick team currently working on COVID. So I will leave it there. Thank you very much.
Thank you. That was great. Any questions for Mike?